In this video on the application of logarithms, we're going to look at the pH scale measuring acidity versus baseness. We read, in chemistry, the acidity of a water-based solution is measured by the concentration of hydrogen ions in the solution in moles per liter. The hydrogen ion concentration is written H+. The measure of acidity used is pH, which is the opposite of the common log of the hydrogen ion concentration. So once again, using logarithms to describe this because as you see, the numbers that you work with as far as hydrogen ion concentration are really tiny. And it's easier to think about numbers like, hey, it's a 3 on the pH scale or it's a 10 on the pH scale instead of thinking about them in terms of, tiny numbers in scientific notation. So more acidic solutions have higher hydrogen ion concentrations and lower pH values. So an example, just a little picture of the pH scale, 7 being neutral, anything less than that would be acidic, anything higher than that would be considered a base or alkaline in nature. So some especially sour vinegar has a pH of 2.4 and a box of leg and sickle, which is funny because it's not Arm and Hammer. Baking soda has a pH of 8.4. So first question, what are their hydrogen ion concentrations? Well, according to the formula we see here, your pH number is equal to the opposite of the common log of the hydrogen ion concentration. So we'll do the sour vinegar first. 2.4 being the pH number, that would be equal to the opposite of the common log, base 10 that is, of the hydrogen ion concentration. So we're going to solve this equation for the hydrogen ion concentration. Before we do that, I'll set up the other one as well. The other one's going to be 8.4. It's the pH number for leg and sickle baking soda. And that's equal to the opposite of the log of the hydrogen ion concentration for that particular compound. So as we solve for H plus in both these, we'd make the other side negative. So I get negative 2.4 equals the positive log. And then I can either solve this by exponentiating both sides, or I can just think about rewriting it as an exponential expression instead. If it's a common logarithm, it means that it's a base of 10. So I could rewrite this, or again think about raising both sides to the exponent with a base of 10. So here, my hydrogen ion concentration for the acid is going to be 10 to the negative 2.4 power. Okay, and we'll come back to that in just a second. We'll do the other one, same thing, make the other side negative, so negative 8.4 equals the log of the hydrogen ion concentration. A little sloppy, but you get the idea. And then raise both sides to the exponent with a base of 10 to undo the logarithm. So there, my hydrogen ion concentration is going to be equal to 10 to the negative 8.4. Okay. Now, to give me an idea of what those numbers are actually like, I'm going to type those into the calculator just for a second. So the hydrogen ion concentration, when I go 10 raised to the negative 2.4 power, that is going to be 0.00398. I'm going to go with 3.98 times 10 to the 10 to the negative third, we'll say. So 3.98 times 10 to the negative third. And that's how many moles per liter we have of hydrogen ion concentration. 3.98 times 10 to the negative third. Okay, so again, that's a pretty tiny number. Like I wouldn't want to talk about 0.00398, but now watch what happens when I take 10 and raise it to the negative 8.4, which is the other expression. And that's going to be 3.98 times, that means times 10 to the negative ninth. So I'll write that in. And I'm going to have 3.98 times 10 to the negative ninth, which is a really tiny number. So again, it's much easier to describe this particular baking soda's acidity or lack thereof as having a pH scale of 8.4. That's a number that seems relatively easy to work with. So pH numbers of 0 to 14, like those are easy to work with, as opposed to working with numbers that are something times 10 to the negative ninth, times 10 to the negative third, whatever teeny tiny decimal numbers that we have really close to 0. So these would be their hydrogen ion concentrations in moles per liter for both of these. Now, letter B asks, how many times greater is the hydrogen ion concentration of the vinegar than that of the baking soda? Well, then we'd be comparing those two numbers. Both of them have 3.98, so I'm going to ignore the 3.98 aspect of it. And I'm going to just compare the 10 to the negative third to 10 to the negative ninth. So I'm comparing the vinegar to the baking soda. And I notice that because both these have the same base, again, I can just compare their exponents instead. It turns into kind of an order of magnitude type problem, which essentially, again, letter C is asking by how many orders of magnitude do they differ? Well, that's going to be 6. So because my order of magnitude difference, to again answer letter C, my order of magnitude difference is 6. What that means is that if I have an order of magnitude of 6, the vinegar's hydrogen ion concentration is 10 to the 6th times greater. And 10 to the 6th is actually 1 million. So it's 1,000,000 times more acidic going from a 2.4 to an 8.4 on the pH scale. So if I go from like say a 1 to a 7, that's 1,000,000 times, or 7 to 1, I should say, it's 1,000,000 times more acidic. Or from a 12 down to a 6, well, that's 1,000,000 times more acidic because I'm changing by that many hydrogen ions in those particular solutions. So in any case, again, easier to work with numbers on the pH scale thanks to logarithms and thinking about things in terms of exponents as opposed to thinking about them in terms of really tiny numbers in scientific notation. So hope that helps.